So welcome to Everyday Mathematics. Today we continue on this wonderful topic on Fourier series, and we'll look at a couple of examples and show how powerful this topic on Fourier series is really before we proceed to later topics like how a Fourier series could be used in curve approximation and things of that sort. So without much ado, we'll move. So before we proceed, let's just remind ourselves what Fourier series is all about. What Fourier series tells us is that if we do have a periodic function fx within the interval negative pi to pi, then we can come up with a imposition or a combination of cosine nx and sine nx, where n straddles from 1 to infinity, and also a constant a naught over 2, and this would approximate our periodic function. So how do we obtain a naught? If you spread out these cosine nx and sine nx terms, since these are periodic, we have negative and positive lobes of equal numbers. You realize that if we integrate them, a naught would be left out, and a naught would be 1 over pi, the integral from negative pi to pi fx. And the same thing applies when we multiply with cosine nx of a given n, and using the principle of orthogonality, since cosine nx and cosine mx are orthogonal to one another, and if you integrate them within the interval negative pi to pi, then you get 0. Then we should be able to also obtain an in the same format. And similarly, bn could also be obtained in this way. So what essentially these expressions are telling us is that if you get any periodic function and then you use this expression, you could come up with a combination of these trigonometrical functions of varying n terms that would give you an approximation of that function. So that's all. So let's look at a few examples. The first example that I wanted us to look at is the, let's say, absolute value of x that's periodic within negative pi to pi. And how do we plot that out? So as you can see, within the negative domain up to negative pi, it increases in the same way as it does on the positive side. And so that when you allow it to repeat itself, you get such an expression where we have 2 pi here, I mean rather 2 pi here, and so on and so on. So that is what we're going to look at. Let's try and see how we may be able to obtain the Fourier series for such an expression. So a naught, we saw a naught to be 1 over pi times the integral from negative pi to pi of fx, where fx is the absolute value of x. And so that means since the positive and the negative lobes are the same, they're pretty much symmetric. We have 2 over pi, and then we're integrating from 0 to pi. And that becomes 2 over pi, integrating x becomes x squared over 2, interval 0 to pi. And so our a naught is going to be pi, as simple as that. And then an is 1 over n times the integral from negative pi to pi of fx times cosine nx. And so applying the same thing here, we in place of fx, we have absolute value of x. And what does that mean? It means that since it's symmetric, we can just say the same as twice. 1 over pi times the integral of from 0 to pi of x cosine nx. And we can use integration by parts here, where we express cosine nx as the derivative of sine nx over n. So integration of u times the derivative of v is the same as uv minus v times the integral of v times the derivative of u. And that's what we've done. So our uv is this times this, which is x times sine nx over n, 0 to pi, minus now we have to differentiate x and then multiply by this. Now, integration by parts is something that if you have any question in regard, please reach out to us. We can always spend some time and explain it in a separate video. So we've put this constant out. Now we have to look at the limits when x tends to pi. This entire thing goes to 0 since sine n pi is 0. When x tends to 0, this also tends to 0 since sine of 0 is 0. And so we just substitute it in, but as you can see, this goes to 0, this goes to 0, and then we're left with this. So that becomes, we're left with 2 over pi times negative integral 0 to pi over sine x over n times the derivative of x. Derivative of x is 1. So our integral now has reduced to negative 2 over pi, integral from 0 to pi of sine nx over n. So integrating this part here, we get negative cosine nx over n squared. And so this negative and this negative multiplied together becomes a positive. And so we have 2 pi cosine nx over n squared. And so substituting the limits, we have cosine n pi minus cosine n0 over n squared. Cosine n pi is the same as negative 1 to the n, because when cosine n is even, this becomes 1. When cosine is odd, this becomes negative 1. And so we factor that in, and our expression becomes 2 over pi negative 1 over to the power n minus 1 over n squared. So, and then what about bn? bn is 1 over pi times the integral from negative pi to pi of fx sine nx. And when we put this in here, it means that in the negative side of things, we have negative x to make it positive. So when x is negative, we have to append a negative sign so that the absolute value becomes a positive. And that's what we've done, and we've separated our integral into two components, from negative pi to 0 and from 0 to pi. And then what happens is that when we make x negative, this negative disappears, but this negative inside the sine x propagates out, so we are negative, but also dx becomes a negative. So those two cancel out, and the expression becomes like this. Now to flip this interval, we have to append a negative outside. So we see that we do have two integrals, one with a negative sign. So this and this would cancel, and so this becomes 0. So bn becomes 0. And so what does that mean? That n naught is pi, n is 2 over pi, negative 1 to the power n minus 1 over n squared, and then bn equals to 0. So what this means is that when n is even, this entire expression becomes 0, and that means that we can now focus on only the odd terms. So since our initial expression of the Fourier series for a function fx that's periodic within negative pi to pi, we see that the absolute value of x can be expressed as pi over 2 plus 2 over pi, n naught over 2, that's pi over 2, times, now we have put 2 over pi, summation, we have kept this constant in because it depends on n, so negative 1 to the power n minus 1 over n squared times cosine nx. But we said we wanted to look at it when, because when n is even, then this degenerates, this reduces to 0. So what about if we just say let n be 2k plus 1? So this is another way we could express it. Pi over 2 minus 4 over pi, summation from k equals to 1 to infinity of cosine 2k plus 1 x over 2k plus 1 squared. And that is our answer. We're going to see how this expression approximates absolute value of x that's periodic. And we're going to keep capital N as our limit, and we see how when we increase our upper limit on the summation side, how does this summation here approximate the absolute value of x. So let's look at it. So you see, we have that, and then this is our expression. Now, capital N up here, when N is 1, we see it's more of a sinusoidal. As N goes up, you see how it approximates the triangular plot that we had originally. So the blue here, the light blue here, is the Fourier series. So you can see that by just using a combination of cosine, here we have cosine terms of different or odd integer values, positive integer values, we can approximate this expression, the absolute value of x periodic, by this interval here. So that's our first example. We'll go and look at the next example. So example number 2 is just this parabolic function that's also periodic within this interval, and this is how it looks like. And then if we allow it to repeat itself, it will look like something like that. So how do we go about doing that? So the first thing we would do is, since a naught is 1 over pi times the integral from negative pi to pi of fx, we'll just plug in the x squared within that. And then so we have, since this is even and or it's symmetric about 0, or x equals to 0, and we're going to get twice 1 over pi times the integral from 0 to pi. And that means that we have 2 over pi times x cubed, integrating x squared is x cubed over 3, and we have the limits applied there appropriately. So this becomes 2 over 3 pi squared. Okay. Then an, as we saw previously, 1 over pi times the integral of fx cosine nx from negative pi to pi. We plug in place of fx x squared, and then now we're going to try and use integration by parts, where cosine nx is going to be the same as the derivative of sine nx over n. But also, since this is symmetric, since cosine nx is also symmetric about 0, we now just take twice the integral from 0 to pi. And so, as we can see, integration by parts here, we have uv, which is x squared times sine nx over n, and then minus sine nx over n times the derivative of x squared. Substituting in pi and 0, we see that this will go to 0, this would also go to 0, and eventually we'll be left with that. And so we have negative 2 pi derivative, the integral from 0 to pi of sine nx over n, derivative of x squared is 2x. And then so we can pull the 2 out. We have 4 over pi n. We've pulled the n out, and then we can re-express nx as the derivative of negative cosine nx over n. We can pull the negative out, and negative times negative, that becomes positive. So we have 4 over pi n squared times the integral from 0 to pi of x times the derivative of cosine nx. Again, integration by parts. We go here we have x times cosine nx, pi to 0 to pi, minus the integral from 0 to pi cosine nx times the derivative of x. Okay, and so substituting in whatever we have here, we have cosine n pi times pi. This becomes negative 1 times pi. This becomes 0 because we have this 0 out here, and then we have minus the integral from 0 to pi of cosine nx, since the derivative of x is 1. And so we can integrate this, and it becomes sine nx over n. As we can see very quickly, that in substituting in the limits, the sine n pi is 0, sine n 0 is 0, so we are left with pi times negative 1 to the power n times 4 over pi n squared. And so our an constant is 4 times negative 1 to the power n over n squared. Bn is going to be like this, and x squared, since this is symmetric, we can probably split the integral into negative pi to 0 and pi 0 to pi. And so we're just going to show that since these two integrals are the same but opposite in sign, we can cancel this, and this bn becomes 0. So essentially, a0 is 2 over 3 pi squared. An is the same as 4 times negative 1 n over n squared, and then bn is 0. So since this is our Fourier series expression, what that means is that x squared, that is periodic, would also become pi squared over 3. That it means 2 pi squared over 3 divided by 2, which is pi squared over 3, plus, pull the 4 out, negative 1 to the power n over n squared times cosine nx. And so if we go ahead and plot this, we'll see how quickly it approximates our expression of the Fourier series. So when n is 1, it's more like sinusoidal, and as you increase n, the capital N, you see how quickly it approximates our parabolic function, our periodic parabolic function. So that's the quick illustration of our Fourier series for that parabolic function. So we have one more example, and then we close this series. So example number 3, which is a function that is like x, but it's more of a fancy x, but it's x over pi minus 1, and it's periodic between 0 and 2 pi, so that when we plot it, it's going to look like this when x is 0. So we have negative 1, and then it increases up to positive 1 at 2 pi. Okay, and so that when it's periodic, it looks like that, right? So n naught is going to be the integral of fx from negative pi to pi times 1 over pi. And so we've plugged in x over pi minus 1 in place of fx here. And that becomes 1 over pi squared, x squared over 2, the limits here, minus 1 over pi times x. And that becomes 4 pi squared over 2 pi squared minus 2 pi over, so which is essentially 2 minus 2, which is 0. So an, as we have expressed previously, is as shown here. Then in place of fx, we've plugged in x over pi minus 1. And so what we do, as usual, I would just separate. And what's important to note here is we are beginning from 0 to 2 pi. We've separated this into two separate integrals. And we've pulled out this 1 over pi out, so we have 1 over pi squared, the integral from 0 to 2 pi of x times cosine nx is the same as the derivative of sine nx over n with respect to x, okay, minus 1 over pi, integrating this cosine nx, the same as sine nx over n. And we don't want to really labor this or belabor this too much. As you can see, at the upper limit, sine 2n pi is going to be 0. At lower limit, sine 0 is going to be 0. So this entire enterprise just goes to 0, and we're left with now this first term here. And as we can see, using integration by parts, we have x times sine nx over n, 0 to 2 pi. And then we have sine nx over n times the derivative of x integrated from 0 to 2 pi. Again, plugging in the limits, this goes to 0, this goes to 0, and we're left with only that. Since we have this, these guys go to 0, and we're left with just this integral here, negative 1 over pi squared times the integral from 0 to 2 pi of sine nx. Can now integrate this, and we get negative 1 over pi squared, negative cosine nx over n squared. And what we see here is cosine 2n pi is 1, cosine n0 is 1, so 1 minus 1, this just becomes 0. Okay, so a0 is 0, an is 0, and now bn is our last hop. So we do the same thing, we do the same process. Now in place of sine nx we have, cosine nx we have sine nx, and so using integration by parts here, we're going to get negative x cosine nx over n, 2 pi, and as we know that this part would go to 0, so we're only focusing on this initial part, and so plugging in the 2 pi at the upper limit and 0 at the lower limit, this goes to 0 because of this 0 here. And then here we have 2 pi cosine n pi. This becomes 1 over n times 2 pi. So we have 2 pi, and obviously it's negative over n. And then we have this integral that has remained, the integral of cosine nx over n. So this becomes negative 2 over n pi plus integrating this, we have 1 over n squared times pi squared times sine nx. Now with the limits 0 to 2 pi, sine of 2n pi is 0, sine of 0 is 0. So this second part just goes to 0. And so what we're left with is just negative 2 over n pi. So we've seen that a0 is 0, an is 0, and bn is negative 2 over n pi. And since this is our general expression for the Fourier series, it means that our x over pi minus 1 is equal to negative 2 over pi, the summation from n equals to 1 to infinity of sine nx over n. So let's see how this, it quickly converges to this Fourier series quickly converges to what we see on the left hand side. So as you can see, we have our lines here, and then now we begin plotting this expression with the limit 1, 3, 4, and as you can see, it quickly approximate. Now this ringing here is what we call the Gibbs effect, but we won't deal with that. I think it's less of our interest for now, but let's just see how it quickly approximates. At n equals 19, it's fairly close, but obviously with these oscillations at the transition point, or the points where we have this drastic change. But all the same, I think this would be a quick illustration that would help someone see how we can use a combination of cosine nx and sine nx terms to approximate periodic functions. So in the next video, we'll look at how we can use this Fourier series to approximate curves. Yeah, take it from there. Thank you so much. Without much ado, we'll come to the end of our video today. If you have any question, please feel free to reach out to us. Would love to hear your take and thought on how we've done, and also if you have any suggestions on how we can improve our videos, we welcome that feedback as well. So until next time, bye bye.